Okay, so today I'm going to do some chemistry. What I have over here is some red cabbage in a glass, and I'm going to see if I can make an indicator out of this. One of those classic indicator experiments from, I don't know, sixth or seventh grade. I'm not really sure, but the reason I'm talking like this, kind of whispering, is because my mom is asleep right now, and I do not want her to wake up and find me doing any of this. So, well, the next step in this experiment is to add some boiling water into this glass. So, that's what I'm going to do right now. Alright, so I have some boiling water over here, and I'm going to slowly and carefully pour it into the glass. Now, red cabbage, like many other plants, contain anthocyanins, and these anthocyanins are what give them their reddish purple color. And what this boiling water is gonna do is extract those anthocyanins from the leaves, or like the plant, and those anthocyanins are going to get into the water. Then I'm going to filter the plant matter, and what I'm going to left with is water with anthocyanins in it. Alright, so I've let this cabbage water sit for about 30 minutes, and I think it's time to start pouring it and filtering it into this other glass that's also containing water. That'll do it. Now what I have over here is some dilute cabbage juice, but the real magic happens when I pour it into these 4 little vials I have over here. Now in these containers I have solutions of different pH, and I'm going to pour this cabbage juice into each one of them to see what happens next. Okay, so I'm going to take this syringe and take some of the cabbage juice out. And pour some into each of these vials. I need some more. Well, the last one's a bit green, as you can see. So what happened? This over here was baking soda solution, which, as you can see, or maybe not, it's not that clearly visible, but it obtained a bluish tint, and that is because baking soda is alkaline. And this one, which is more green, was basically laundry detergent, which has a slightly higher, or not really slightly, but a higher pH than baking soda. Now, these two are acids, and this one was vinegar, and it's got a pinkish red color after I poured some of the cabbage juice into it. And this one was lemon juice mixed into water. So let's put the acids together and the basics of solutions on one side. Okay, so what is apparent over here is that introduction of anthocyanins from red cabbage into these aqueous media of aqueous solutions of acids and bases induced a change in color of the indicator, which the red cabbage juice was. But what really is going on over here? So basically, most indicators that we use are weak acids or bases, which means that, well, let's denote an indicator that is acidic as HIND for indicator. This is an acidic indicator. When we add it to an aqueous media, let's just say liquid water, we get as reactants, we see that this hydrogen over here dissociates from the indicator to form H plus ions with water and some conjugate base. This is our conjugate base. Well, after that, the H plus ions and the water can simply form hydronium, but that's not a concern for now. Likewise, if we have a basic indicator and we add it in aqueous media, we'll get, well, water, a conjugate acid this time, and some OH minus ions because the OH dissociates from the indicator. So let's focus on this reaction right now. Here we have our indicator in two forms. One form is the acidic form which we added as our reactant, and the other form is the conjugate base which we get as a product. So let's assume that this reaction is at equilibrium. Which means that the concentration of the products I'm not going to write water here because that doesn't matter, divided by the concentration of the reactants is a constant which we call the equilibrium constant. Here I'm going to denote it with Ka. So we can rewrite this equation as H plus, wait, the concentration of the conjugate base upon the concentration of the original acidic indicator equals to the equilibrium constant upon the concentration of the H plus ions. Now we can take these H plus ions, the concentration of the H plus ions, as simply pH, because that's really what it is in the end. So when the equilibrium constant is equal to the pH, then that means that the concentration of the conjugate base is equal to the concentration of the indicator. So both the forms, both the acidic and the basic forms of the indicator are at equal concentrations at this point. But if we change the concentration of the H plus ions, if we change the pH, then we change this ratio. We change the ratio of the conjugate base upon the original acidic indicator, and that is what changes color. How exactly does it change the color? Well, we know that the conjugate base has a different structure to the with respect to the original indicator. And this is because, well, there's a lack of a proton in here. It loses an H plus ion. And because of this, these two have different absorption spectra. And what that means is basically they absorb different wavelengths of light and reflect different wavelengths of light because of their structure. And that results in a change in color. And that is basically how acid base indicators work.